My name is Caleb Johnson, and for the last year, I've had the pleasure of working with Dr. Vasileios Anagnostopoulos and Zachary Murphy on our project, which was a mechanistic study into the bonding of a variety of ligands with uranium. In this case, we were looking at uranium in the form of studtite, which is a uranium mineral commonly found in nuclear waste tanks. This study was actually based on a previous study conducted by Dr. Anagnostopoulos and Zach Murphy, and it was a similar theme. They were looking into the bonding of these two ligands, specifically EDTA and HEDTA, with, again, studtite, uranium in studtite. And the purpose of that experiment was concerned with the storage of nuclear waste currently, which the strategy right now is we put nuclear waste in these long-term storage tanks, we bury them deep underground, and we either wait for a better method of disposal or potentially we wait for methods of recycling them. Either way, they are stored underground for long periods of time, and a common issue more and more as these tanks get older, they fall into disrepair, they have poor maintenance, is they leak. They leak these toxic radioactive chemicals into the environment, and the concern is that HEDTA and EDTA, which are byproducts of nuclear reactions, they are in these waste tanks with studtite. The concern on that first project was, do these ligands make the uranium more soluble? And because that's an issue if the tanks leak and there are HEDTA, EDTA making these uranium atoms more soluble, they are leaching into the environment farther and faster. So they were looking into those, and following the results of that project, they developed an interest in the mechanistics of that bonding of the ligands with uranium. And the question was, what is it about the structure of these ligands which determines how fast they bond with the uranium and their solubility from that? And the idea was, the hypothesis that they came up with was, these ligands are forming cyclic bonds with the studtite. We know that. So the question is, or the hypothesis was, I should say, these shorter ligands are forming these cyclic bonds faster than the longer ligands because they have less freedom around. They're short, they are flowing around, they're bonding faster. The long ones have a lot more freedom, they have a lot more space to move. They're going to take a longer time to bond with that uranium and make it more soluble. So, going based on that, a panel of 7 ligands was selected, and those ligands were oxalate, malonate, glutarate, succinate, adipate, aminodiacetate, and diglycolic acid. And the reason for choosing those ligands was, as you can see from the first 5, I've included a little graphic here. They are increasing in length as you go along, basically by one carbon-carbon bond, because all these ligands are hydrocarbon chains with basically deprotonated carboxylic acids at the end. So the question was, do these longer ligands take a longer time to bond? Why, in that case, do we have aminodiacetate and diglycolic acid here? And that is because this project, like I said, is a further inquiry into that first project. And these two ligands have structures similar to the structure of EDTA, which I've also included here. And really, since we're just kind of looking further into that, we wanted to include those because we wanted to know more about the mechanistic results of this study, how that relates to these ligands, which are closer in the structure to EDTA. So going based on that, the decision was to conduct batch dissolution studies of all these ligands. Basically, we would take 1 milligram of solid studtite, put it in a vial with multiple solutions of each ligand, 40 milliliters of each ligand in solution, and mix them for long periods of time, measuring them like constantly. To do that, we would take these vials, centrifuge them, take a little bit of that liquid phase off the top, making sure we didn't get into that solid studtite. Then we would run that sample through the ion chromatograph IC and the inductively coupled plasma mass spectrometer. So the purpose of the IC was to determine the concentration of the ligand in the solution, whereas the ICP-MS was to determine the concentration of the uranium, because we wanted to see over time how much of that uranium was making its way into the liquid phase. Before we started that batch dissolution study, what we needed were accurate calibration curves for the IC, because we needed to determine things like what eluent to use. It's going to vary based on the ligand. And we needed to determine the elution times. We needed calibration curves to determine our limits of detection and quantification so we could decide what concentrations we were looking for in those batch dissolution studies in the liquid phases of the solution. So we took these ligands, we ran them through the IC, we determined their proper eluents, which in the case of all the ligands except for immunodiacetate IDA was 35 millimolar sodium hydroxide. Immunodiacetate, we had some issues with. We ended up having to lower the concentration of that eluent to 25 millimolar NaOH, and that worked just fine, so we stuck with that. Following that, we ran calibration curve samples for every single one of these ligands, and as you can see in the table I have here, we have marked down the eluent that they used, which, like I said before, 35 millimolar for all of them except IDA. We've got their elution times, the R squared value for those calibration linear trend lines, which very, very high for all of them. So great uncertainty. And I've got the linear equations that we were going to use for the batch dissolution studies, as well as our limits of detection and limits of quantification. Highest limit of quantification was for oxalate. That was 42.10 micromolar. That's actually very good. We are not going to be studying concentrations lower than that, so that was no problem. And I've included here a little graphic, a linear graphic of one of our calibration curves. This one's for succinate. And as you can see, there's very little deviation of the trend line from those data points. We've also got a chromatogram of the elution of succinate. As you can see, if you look, actually, there's a peak here for succinate. We've also got one for nitrates. And the reason we included those in the sample was because we're going to use nitric acid to balance out the pH. We used nitric acid and sodium hydroxide. Sodium hydroxide was the eluent. We weren't really concerned about that showing up. We were concerned with those nitrates showing up and possibly affecting the peak area, perhaps messing with our calibration curves. So we just ensured when we were doing it, we included nitrates to make sure that that peak was clearly distinct. And then I've also included, like I said, we are only just now getting into the batch dissolution studies. This project is ongoing. It'll probably be going on for another long while. So we've only got a few days of results and only for 4 of the ligands. But I've included it because, as you can see here, this malonate, our shortest ligand included in this sample set at least, is performing much better than the rest of the ligands. It's got a much higher concentration of uranium in the liquid phase than the rest, which is very good for our hypothesis. Our hypothesis supports it, and that is looking good. And that is really all we have so far. I've got all the information from those calibration curves. We're just now starting the batch studies, and like I said, we're very helpful. I'd like to first of all thank Dr. Anagnosopoulos and Zachary Murphy for including me in their research. It's not an easy thing to trust your research to someone else, especially an undergraduate student. So I really appreciate them sticking their neck out like that. And I also wanted to thank the Nuclear Regulatory Commission for supplying us with an award to fund this research. We wouldn't have been able to do it without their support. So that is all. Thank you so much.